You rolled one coin exactly once around an identical coin, and the answer is 2 turns? Only 3 people out of 300,000 got it right. Let's solve it all the way to the end right now. Grab 2 identical coins. Fix one to the table, press the other against its edge, and roll it once all the way around without slipping. So, how many times did the rolling coin turn about itself? Most people answer without hesitation. 1 turn, obviously, because the distance rolled equals the circumference of the fixed coin. But the answer, surprisingly, is 2 turns. Take out 2 real coins and roll them yourself. When you watch the design on top stand upright twice, it's a head-spinning experience. This phenomenon, which runs head-on against intuition, is exactly the coin paradox, the rolling coin paradox. Mathematically, it's just a calculation of curve length, but the gap with physical intuition is so wide that it has thrown countless people into confusion. There's a legendary incident that shows just how powerful this paradox is. In 1982, this very principle appeared on the math section of the SAT, the U.S. college entrance exam. More than 300,000 students took the exam, yet only 3 of them got the answer right. It wasn't because the problem was too hard. It was because the correct answer wasn't among the choices at all. The authors and the reviewers all fell into the same misconception, and so they never put the true answer among the choices. Let's look at the actual problem. Circle A has a radius 1/3 that of circle B. If circle A rolls once around circle B without slipping and returns to its starting point, how many times does circle A turn about itself? The authors reason like this. Since circle B's circumference is 3 times longer, the answer is obviously 3 turns. So they set the answer as choice B, 3 turns. By now you've probably caught on. The answer wasn't 3 turns but 4 turns. Yet there was no 4 turns among the choices. The choices were these: 3/2, 3, 6, 9/2, and 9. The correct answer 4 simply wasn't there. Only 3 students, clever or stubborn, raised an objection. The question was thrown out, and every exam was rescored. Today we'll dig into this curious paradox piece by piece, with hands-on calculation and Python visualization. Before we dive in, let's set the stage. 2 coins of exactly the same size. Coin A is fixed firmly to the ground. Coin B rolls along its outer edge, staying in contact the whole way. Both have the same radius, r. There's just one condition. Enough friction that it never slips, pure rolling only. Here's the question. Once coin B travels all the way around A and returns to its starting point, how many degrees, how many turns, has B itself rotated? The first thing that comes to mind is this. The distance B rolls equals A's circumference, so it rolls out exactly its own circumference, just 1 turn. A's circumference is 2 pi r. B's circumference is also 2 pi r. Since they're equal, it looks like exactly 1 turn. But there's a trap. If B rolled along a flat, straight floor instead of around a round coin, that statement would be exactly right. But our path isn't a straight line, it's a curve, a circle. And this is exactly where intuition breaks down. Run the experiment and B's top design stands upright twice. That's 720 degrees, 2 full turns. Why 2 turns? Think of the Earth and the Sun, and it suddenly becomes surprisingly easy to grasp. Coin B's motion is actually the result of 2 rotations combined. The first is rotation, the spin, the coin turning about its own center. B rolls a distance of 2 pi r while in contact, and its own circumference is also 2 pi r, so it spins exactly 1 turn. The second is revolution, turning about the center of the fixed coin, the hidden turn that intuition so easily misses. Picture this. Coin B doesn't roll at all. It slides around coin A once, always facing the same direction. And by the time it returns to the start, what happens? Coin B itself has turned a full circle in space. That, right there, is 1 revolution. So the total number of turns of B, as seen from outside, is the sum of these 2 motions. 1 rotation plus 1 revolution, that's 2 turns. If you unroll coin A flat into a straight line, B makes exactly 1 turn. Because the orbit is curled into a circle, that curvature adds 1 extra revolution. By the way, the answer to that SAT problem followed the very same logic. 3 rotations plus 1 revolution, that's 4 turns. Beyond the intuitive analogy, let's now nail it down clearly with math. and by two separate routes at that. Both routes ultimately arrive at the same place, the +1. First route. Let the radius of coin A be RA, and the radius of coin B be RB. The path it has to roll along is the circumference of a 2 pi RA. The number of rotations B makes by rolling on its own is the path divided by its own circumference, 2 pi RA over 2 pi RB, which reduces to RA over RB. To this, we always add the one revolution that comes from following the curved orbit. If the two coins are the same size, RA equals RB. 1 plus 1, that's 2 turns. And if RA is 3 times RB, like in the SAT problem, 3 plus 1, 4 turns. Second route. For those who still aren't buying it, the roll distance is 2 pi RA, so why do you get to just add 1? Here's the most rigorous proof. The secret lies in the distance B's center point actually travels. As B rolls in contact with A, B's center stays always RA plus RB away from A's center. So the path traced by B's center is a giant circle of radius r. That's exactly the green dashed circle in the figure. The circumference of this giant circle is 2 pi times the quantity r plus r. So B as a whole rolls through exactly this distance in space. We divide that true travel distance by B's own circumference, 2 pi r. Simplify it and you get r over r3 plus 1. The +1 that was hiding in the formula pops right out naturally like magic. Proof complete. Both paths meet at exactly the same answer. R over R B, +1. Seeing is believing. Now let's roll the coin ourselves in Python and confirm it with our own eyes. The curve traced by a point on a circle that rolls along the outside of a fixed circle is what mathematicians call an epicycloid. The heart of the Python code is just 4 lines, the center of the rolling circle, and the position of the track point on it. The center travels along a big circle whose radius is the large radius plus the small radius, exactly the center path we saw earlier. The track point sits at the spot offset from that center by the rotation angle. And that rotation angle is the key 1 plus r over r times theta. It's the number of rotations plus 1 revolution. First, the equal size coins. We run the code with the large radius set to 1 and the small radius also set to 1. The console prints the expected total number of turns, 2.0. Let's follow how the path gets drawn. First, the quarter waypoint. Past the halfway mark, the red path slowly reveals the outline of a heart. The finished path is exactly a heart shape, a cardioid. And it has exactly one sharp point, one cusp. A cusp is where the rolling point touches the surface of the fixed coin, and its direction of travel sharply reverses. And the number of cusps equals r over r, that is, the number of rotations. So the total number of turns is always the cusp count plus 1 revolution. This path with its single cusp is physical proof that the coin turned twice. Now the SAT scenario. We change the big radius to 3 and the small radius to 1 and run it. The console prints the expected total number of rotations, 4.0. Once you've rolled about halfway, a couple of peaks start to rise. The finished curve has exactly 3 sharp cusps. 3 cusps plus 1 revolution, that's 4 turns, proven crystal clear. Change just the one big radius value in the code, and the number of cusps follows exactly in proportion. When the formula is right, the numbers are right too. The coin paradox was never just a calculation of circumference. On a curved orbit, it's a beautiful piece of physics that resolves only when you see both at once. The rotation, which is the object's own motion, and the revolution, which is the turning of the observer's reference frame. Our brains model the world fairly simply. It's the laziness of intuition, taking rolling along a straight line and applying it unchanged to a curve. That laziness fooled all of us, including the people who wrote the 1982 SAT. This simple two-coin paradox leaves us with a deep lesson. When intuition collides hard with the actual result, the importance of not leaning on imagination alone, but looking at the world again through the rigorous lens of the center's trajectory. Funnily enough, just as the wheel paradox revealed a hidden slip, the coin paradox revealed a hidden +1 turn. Finally, a 3-line recap. 1. 2. It appeared on the 1982 SAT, but even the test writers got it wrong and the correct answer wasn't among the choices. An unprecedented fiasco. 3. The heart of the turning is rotation plus revolution. The total number of turns is RA over RB plus 1. Today, hand a friend next to you 2 101 coins and ask them. 9 times out of 10, that friend will confidently shout 1 turn. Just like the test takers of 1982. If you enjoyed today's journey, support us with a subscribe and a like. We'll meet again at ELLS Lab for the next Math Odyssey.